Welcome back to our video module on quantum mechanics. At the top of the screen, I've written down the Schrodinger's equation, and this will be the basis of our work going forward this semester. However, you'll notice that we're dealing with partial derivatives here, which if we can't find a good way to address these, we're going to be stuck with some truly burdensome math going forward. So one might fairly ask, where do you even start in finding solutions to this equation? Today we'll be using mathematical tools that you already have under your belt to identify characteristics and limitations of separable solutions for this equation. So let's start with a wave that's a function of x and t, and we're going to assume a separable solution where we have c of x times phi of t. Now over here, that's going to mean that our potential is only a function of x and is constant through t, and it'll mean the left-hand side of this equation will be some function of t. The right-hand side of this equation will go to some function of x. And we're going to set both sides of this equation to equal to some constant we'll call e. So to find the function of x, we've divided both sides by c, and we end up with this equation here. Now if we look, we see the v indicates the potential energy. Inspection will show that this term right here indicates the kinetic energy, which means this term, this E, has been craftily chosen to mean the total energy, and if we remember from our classical mechanics, E equals T plus V, which gives us a little more texture on the Schrodinger equation's terms and what they mean. And if we follow the same steps to find f of t, we'd come up with this equation, which leads to solutions of this form, e to the negative iet over h bar. This is known as the Time Independent Schrodinger's Equation, or as I'll often annotate it, just Tise, and it has some really interesting characteristics. First, if we assume a separable solution, the actual wave function is a function of x and t. However, when we're looking at our probability distribution, which is wave function squared, we see that is only a function of x. It's lost its time dependence. Another interesting aspect of it is that we have a discernible total energy, which is easy to identify. And we've been able to kind of isolate the potential profile. And this is going to lead to a lot of our exploration going forward, where we'll look at different potential profiles and how the waves respond given the change in the potential. A third interesting phenomenon is the general solution of the wave equation can be expressed by a linear combination of the time-independent Schrodinger solutions. So you can imagine we have state 1, state 2, and state 3. Now, of course, in this case, I'm putting in equal amounts of each of them, but you can imagine that wouldn't be the case in an actual general solution. We can use linear combinations of our time-independent equations to represent a general solution. And I've written down a more general form of this in summation notation for your reference. So in summary, if we assume a potential that is only a function of x and not a function of t, we can separate our wave equation into x-dependent solutions and time-dependent solutions. This gives us a more nuanced feel of the Schrodinger's equation. It moves our calculus from partial differentials to definite differentials. It gives us an idea of the forms of the solutions. It gives us probability distributions that don't vary with time, and we don't compromise the ability to find general solutions that depend on x and t. And while we've danced around what the time-independent Schrodinger equation's features are and how it functions, it's worthwhile to actually write down the time-independent Schrodinger equation that we'll be working from for the next couple weeks. Thank you for joining me for this brief exploration of the time-independent Schrodinger equation, and I look forward to spending time with you as we explore the separable solutions more fully.